Hey, how's it going, guys? Happy weekend. I'm filming this video for you because, well, this problem set isn't too bad, but you got more of these pesky simplifying radicals problems. Now, they want you to get good at this because you're going to have to take a lot of square roots when you do Pythagorean theorem problems. So, should be pretty smooth sailing, I'm hoping, for this homework. But I heard from you, right, the student, the past few days, that actually some of these square root problems are actually kind of harder this year, right? It's a little bit easier when you have your group there and you're working through them. But maybe you're having a little trouble with this. That's why I figured I'd film numbers 5 through 12. All right, so the two things I want you to keep in mind when it comes to simplifying radical expressions, two things you got to do. One, you got to actually simplify the radicals themselves. This means you should be factoring out any perfect squares. Okay, so the numbers like, well, not one, one's a perfect square, you don't even factor that out. But if you can find a 4 goes into any of these numbers, then you can take the square root of that 4 and then pull a 2 outside. If you can find a 9 goes into any of these numbers, then you can take the square root of that and pull a 3 out and whatnot here. Okay, so anyways, you should have practiced that a couple days ago. And then the other thing was something called rationalizing the denominator. So something like number 11, right? Number 11 right here, we're definitely got to rationalize that denominator. And it might actually happen for us right away, okay? Because we have an irrational number, okay? The square root, if it's not a square root, you can simplify it all. It's something called an irrational number. The square root of 3 is actually an invented number, right? We figure we have a square with an area of 3. Well, what are the side lengths? There's no perfect number for that. It's about 1.7 or so, right? 1.7, about 1.7 times 1.7 is about 3, but not exactly. So this is something called an irrational number. We got to get it out of the denominator. So looks like that'll be taking care of itself. Guys, this is actually super hard, so I don't know how many takers I have in watching this video, but I might as well do it along with you. So make your homework go a little bit smoother in case you're having sitting down and not really wanting to start. You want to watch some examples first. Simplify each expression. Well, this is really easy. Guys, why am I doing these problems? I'm going to do some harder stuff. This isn't even really that much harder. Some basic Pythagorean theorem stuff later. You might be like, hey, Mr. Ford, the problem set wasn't too bad all of a sudden. All right, so anyways, what does this mean? The square root of 5 squared, right? The squaring undoes a freaking square root, right? Remember, the square root of 5, definition of square root of 5 is the number multiplied to itself that becomes 5. So if I do that 2 times, right, that's what the squaring thing does, right? Shouldn't that logically just equal 5? Yeah, you multiply 2 of the same square roots together, it becomes that actual number itself. Okay, good to go there. Next one up here, this one might confuse people, right? You might be unsure of exactly what to do, and I'm actually trying to think of a good way to kind of do it. Okay, here's how I'd kind of recommend the different, remind you of the difference. Then this does not equal. Okay, this does not equal this. It doesn't equal 2 times by root 7 squared. Okay, so what I'm trying to say is that when you have an exponent outside of parentheses, it's going to go to all those little parts that are inside the parentheses if we have multiplication in a row. It's a little bit more complicated when we have addition, which we don't have addition in any of this, and our subtraction, because then you got to do like the FOIL or the generic rectangle, some stuff you've hopefully learned in Algebra 1. But if it's multiplication, this 2, the base of this exponent, remember, an exponent has a base. So if I had it like this with the parentheses like this, I would just square the root 7. That would become 7 multiplied times 2. That would be 14. The answer here is not 14. It's definitely not 14 here, because this 2, way we can rewrite this, way we can think about rewriting this is going to be, right, this 2, this is part of the base, and this is part of the base. They're both bases of the exponent, right? So another way we can think about it too is that this here, 2 times by root 7 squared, is the same thing as 2 times by root 7 times by 2 times by root 7, right? It times itself, right? Squaring it, okay? If I have it like this, I just have a whole bunch of multiplication going on here, okay? Multiplication has the commutative property, right? Which the commutative property is the one where you can reorder multiplication. Doesn't matter what order you put things in if you're multiplying them, right? When multiplying things, 4 times 5 is the same thing as 5 times 4, right? You get the same answer. So anyways, if we put them all together, right, if we move the 2's here and then we move our root 7's here and root 7's here, it clearly isn't going to equal the same thing as what that would equal, which ended up equaling 14. This is going to be 2 times 2, which is 4. 7 times 7, well, that becomes 7 right down here. And then we got 4 times 7, and then this one equals 28. Okay? Faster way to get there is this. This is probably how I'd recommend doing a problem like this, is that you got to remember this here is the whole base of the exponent. So what I could have done, it's actually called the power to a power rule. This is what they call it in Algebra 1 this year. Power to a power rule of an exponent here is that this is going to all these things. This is all the base here. So this is 2 to the first power right here. So I'm going to multiply that by 2, so I can rewrite this as 2 squared. This is root 7, technically to the first power 2. I can do this as root 7 squared, and this is going to be the same thing as I did down here. 2 squared is 4. Root 7 squared, right, just undoes the square root. That's 7 here, and 4 times by 7 equals 28. Okay, so that's one we might have to think about a little bit here. And so I'm happy to have gone through with you, helped you a little bit through the process, I hope. Okay, here's one more. We're going to do it the faster way here. Okay, I got my exponent. Oh, we got parentheses there. Perfect. What's the base of my exponent? This whole thing is the base here. So that means they're all going to get, and it's only because this is multiplication here. It gets harder when there's pluses or minuses. We don't have that here. But this is the base of the exponent. So this is going to be 7 to the first power, 7 to the root 2 to the first power here. Remember, the power to a power rule is that the powers multiply. Hopefully you remember that from algebra 1. If not, you'll review in algebra 2. 2 times 1 would be 2. So 7 squared, and then root 2 squared. Okay, square that up. We get 49. Root 2 squared is 2. 49 times 2 is 98. Oops, not 88, 98. Good to go there. Next one up, right? You gotta practice these things, right? You gotta realize that we're gonna be changing forms, and when things get complicated, right? We've done all these little problems here and got them good to go. Okay, this one here, everything gets squared. Okay, everything gets squared because technically, right? You can always expand it if you want to. You don't have to use the exponent form. You can actually just write it out in terms of how many factors there are, right? This is just this. Right? A squaring means times itself, okay? We have it like this here, and this is going to prove to you that this squaring exponent does go to the numerator and goes to the denominator, right? Because if I do it 2 times, I'm left with this. And remember, when you're multiplying fractions, numerator times the numerator, denominator times denominator. So this is going to be root 2 times root 2 is 2, denominator times denominator is 4, and we get 2/4 as kind of our answer, but we can simplify that fraction. 1/2 would be the answer there, okay? If you wanted to use your shortcuts on that one, because I recommend using shortcuts on that one, remember that when you have an exponent outside of a fraction, that exponent is going to go both to the numerator and to the denominator, right? You pick up on these rules over time, right? It takes practice, takes years of practice in different classes. This goes through, but we got to keep moving, okay? Check this one out here. This one's squared here. What did I just tell you last time? Well, when you have a squaring outside, just think of it. It's that fraction times that fraction. So you're repeating both the numerator and the denominator, right? 2 different times, okay? So what I can rewrite this as 3 squared times root 5 squared if I wanted to. I didn't actually have to expand it out, right? Write the exponential expression in expanded form here. I can just do it like this. 3 squared is 9. Root 5 squared is just root 5. So I get 9 over 5, or 1 4/5. I don't know exactly how they have that in the answer key here in your answers here. Okay, let's keep on going. Why not? 2n squared. Well, that's just 2n times 2n. Very good. 2n times 2n. Well, 2 times 2 is 4. N times n is n squared. So this would be 4n squared. Okay, so this is just to remind you of the product, the power to a power rule of exponents. This is 2 to the first, n to the first, right? And we can multiply our exponents here. 2 squared is 4. N to the first times 2 is 2. So n squared is what we have for the variable component of that here. There we go for the answer there. Next one up, I started this one because, hey, I'm not supposed to write it like that. Remember, root 3 is an irrational number, not a rational number, an EIR, right? When you hear IR in English, it often means the opposite of that, right? Irrespective. Is that even a word, irrespective? I think that's a common fallacy is the word irrespective is not a word. Let's actually Google that real quick here. I Googled in class earlier today. Is irrespective a word? Let's see here. Oh, it is a word. There we go. Yeah, so people debate this thing here. It's like, is this actually a thing? All right. I don't know. I'm a math guy. You might be laughing at me right now because I didn't know that word. That word is actually a word here. Anyway, n squared over root 3 squared. This is actually pretty easy. N squared over 3. So I'm choosing some pretty easier problems to do with you guys here. Hang out with me. To do it here. We got it. N squared over 3. That's as simple as we can get here. Last one is up here. So guys, these weren't too bad, were they? If they were the other day, hopefully this was a little bit easier, so I'm doing along with you here. We got this repeated 2 times, right? Repeated 2 times. So you could expand it if you want. If you're squaring these freaking things, you can just expand them like this to just sanity check it Okay, I got a whole bunch of multiplication here. I got a whole bunch of multiplication here. Multiplication has the commutative property, right? Order does, when you're old, multiply something, order does not matter. So you can shake it up, you can move it around, right? It also has the associative property. It doesn't matter how you associate things with these parentheses, okay? So we can even drop all parentheses and just multiply them. So I'm sort of using the associative property and the commutative property to move these up front, drop how we associate them, drop our grouping, that is, here. It doesn't matter how you group things if you're just multiplying stuff. That's what the associative property is. Commutative properties, you can move stuff around. The factors, you can multiply them in different orders. So this is 2 over 3 times 2 over 3 times by root 6 times by root 6. What do we know by root 6 times root 6? Well, that's just 6. What do we know about 2/3 times 2/3? Well, that's 2 times 2. Remember, numerator to numerator times denominator to denominator, so we get 4/9. Okay? 4/9 times by 6. 4 times 6, so this would just be 6 over 1, right? We can change that to a fraction if we want to. Make our lives easier, just pretend we're multiplying true fractions. 4 times 6 is 24, and over 9, that's going to get me, right? So this equals 24 over 9. I'll just put that down here, and let's get it as a mixed number. So 9 times 2 would bring me to 18, and I'd be left with 6/9 after that. So I got 2 2/3. I hope that's right. I'm not going to check the answer key because I like when you tell me I made a mistake, or I just like, I probably won't even update this video if I made a mistake here. We'll just take it. Let's see. That's 2, 6. Yeah, I think it's right. We'll see. All right. Anyways, wrapping up here. Man, some of this homework go really quickly potentially. So I figured I'd do these ones with you because again, the goal of today's class was just to prove the Pythagorean theorem in one of the nearly 400 ways. I think there's more like 500 ways, to be honest, ways to prove the Pythagorean theorem. So we spent time doing that today using that geometric mean strategy of drawing the altitude to the hypotenuse. We got there. Hopefully you got there. You do have to submit a picture of your proof. Just verify that you did it along with us here as part of your homework. And we did that. We talked about some of the visualizations of how this here, this is a right triangle. So this here, okay. So we talked about this here. 10 squared would equal, right? 7 times 7, 49 would equal this here, right? We could fit this x squared and these 49 units into this. Well, this would be 100 units right here, okay? I wouldn't solve these problems quite like this. I would just use the freaking Pythagorean theorem, right? I would use a squared plus b squared equals c squared. Why, again, are we allowed to use a squared plus b squared equals c squared in this particular diagram, in that particular diagram, that particular diagram? Well, what kind of triangles are these? These are all right triangles, okay? All right triangles. So your triangles need to be right triangles to be eligible to use the Pythagorean theorem. Don't make the same mistake as the scarecrow from The Wizard of Oz. I think he said isosceles triangles in there. He also made another mistake too. Probably watched that at some point here. The got to be right triangle, and the sum of the squares of the lengths of the two legs of the right triangle is actually equal to the square of the length of the hypotenuse of the right triangle. Neat. And this appears in all different permutations throughout math. This comes up a bunch. It's one of the most important mathematical formulas, up there with the quadratic formula and up there with a whole bunch of other stuff here. So anyways, you're just diving into it with us here in ninth grade. You should have done a bit of this in middle school too, though. I'm hearing from you guys. You're like, I already know Pythagorean theorem. Come on, let's just do it we proved it at least in class today. So let's check this one out here. You guys are sick of me hearing me talk. I know you're not getting a lesson from me this weekend. Sad. So let's just get this thing done here. We got 7 squared is 49, x squared is here, 10 squared is 100. Okay, so I would just set this up in the freaking formula, Pythagorean theorem. Put it in the, people say, hey, put it in the Pythagorean theorem. This is what they're talking about. It means put it in the formula. A squared plus b squared plus c squared. A leg squared plus the other leg squared, length of the leg, right, that is here, equals the length of the hypotenuse squared. So 7 is a leg, x is a leg, right? Just figure out where they all go, right? My legs go in the A and B spots. My hypotenuse goes in the C spot. And now I can solve this one here. So square everything, right? Square it on up. Okay, then we get x squared equal to, I got to subtract that 49, so I'm going to bring the 49 over here. So 100 minus 49 is 51. You with me? All right. Let me know if I can meet to go over some stuff like this here. And here, what we notice here is that we're not going to be able to reduce this one. Let's see here. Take the square root of both sides, right? We want to isolate x. We want to figure out exactly how long this is. And we take the square root of both sides. And yeah, I mean, root 51 No perfect squares go into that. You can go through them if you want to. Well, 1 goes into it, 1 and 51. But you can't. There's no reason to factor out a 1. You still have root 51 left. 4, right, only goes into even numbers, so it's not going to go into 51. 9 would go into what? 9 goes into multiplication tables. It goes into 45. There we go. And it goes into 54. Doesn't go into 51. 16 is the next one, 4 squared. 16 would only go into even numbers. We can throw that one out. What else? What's next here? 25 would go into 50, not 51. And 36, yeah, doesn't go into goes into 72, meets in 49 is pretty close to 51, but double it 98. So 64 would be the next perfect square. So yeah, no perfect squares go into that 51. So that's as simplified as when you write the answer. So that is it, square root of 51. So it's approximately 7 or so, right? 49 is the square of 7. 51 is just a little bit higher than that, right? It's between 7 and 8. So nearly isosceles, this triangle. Look at this. I mean, they drew it. It looks kind of isosceles to me. Is it isosceles though? No. Square root of 51 is larger than 7, right? The square root of 49. So it's not an isosceles triangle. You can deduce that, right? So that's a good question, actually. I'd ask you, like, is this an isosceles triangle? And you can prove something's isosceles kind of just by doing the Pythagorean theorem of a problem like this. Interesting. All right, next one up, we have number 14. So again, a squared plus b squared equals c squared. Figure it out, right? Let's make this one a. Let's make this one b. Let's make this one c. The important thing is that I made the hypotenuse c. That's the big guy, right? That's the big longest side in a right triangle, because it's opposite the largest angle, right? A right angle here. So hypotenuse is always the longest in a right triangle. So that's going to be equal to the sum of the squares of the two smaller sides, the two legs right here. So let's go ahead and jam it on into our formula. 4 squared plus 6 squared equals x squared, right? We're putting x there instead. We get 16 for 4 squared. We get 36 for 6 squared. So hopefully you get good at these perfect squares. You should be able to do that really, really, really quickly. Push yourself to do it. In the meantime, get a calculator out, right? Do it super quickly. Don't get left in dust, okay? Always have a calculator out in math class in high school, right? You're too old to not have the calculator out, okay? You got to be able to do that really quickly, okay? And your brain will follow from there, right? In case you're pretty slow with this. If you do it enough on the calculator, you'll get it, right? You'll follow the patterns. Just keep an eye out for patterns here. We're just going to get through more problems, okay? 16 plus 36, well, that's pretty close to 51, huh? That's 52. This one, a perfect square would go into this one, though, so let's check it out. Okay, so there we go. Next step, when I have an x squared and it's equal to a number, it's just going to be a positive number, right? So that's another thing too, that 52 would technically have 2 square roots, a negative and a positive, right? Because 2 negatives can multiply to each other to become 25, for instance, right? Negative 5 times negative 5 would be 25. So negative 5 has 2 square roots, 5 and negative 5. 52 would be the same thing, but they're both irrational. So anyways, we just care about the positive, okay? We just care about the positive values only. Values only in geometry, right? Because we're dealing, right? I mean, pretty much like, unless they give you an algebra question in geometry, but what we're dealing with is a positive length, right? Distance is always positive, right? The ruler postulate puts us, every length is greater than 0. I believe there's something there, the ruler postulate about segment lengths. But anyways, so you get this here, you got to solve for x, so to figure out what the length is here. Sure, it's square, right? It's square here. It's pretty close to this square here, right? This was a 51 square. This would be a 52 square, so it's slightly larger. But we got to find the square root, right? The square root, this side here. So the square root of 52, square root of 52. There's some perfect squares that go into it. So recommendations on your video that you heard before, 2 goes into this because it's an even number. So 2 times by 26 would be 52. Can we get another 2 out of there? Yeah, we can. We can do this. We can do square root of 2 times 13. Am I correct here? Okay, so the one strategy of this to simplify your radicals is just figure out how many times 2 goes into it, right? How many times is 2, or how many times 3 goes into it? 3 doesn't go into this one, but you want to figure out ways we can get multiple factors that go into that, because then you can take the square root of just this section, for instance, here, okay? Square root of 2 times 2. Well, 2 times 2 is 4. Square root of 4 is 2. Okay, so this is going to equal x. Square root of 2 times 2 is 2. So we can pull out, right? Pull out that 2, and this is going to give us our simplified radical form answer, which is what we're looking for this year from the practice that you guys had for simplifying radicals. triangles, okay? Might require more practice. I think the best video for you guys potentially to watch is that sort of 18-minute video from that female MIT grad, right? So she promoted herself here, but she actually goes through it. Check this list. It might be easier than this. Check the list here of numbers that go into 52. Does one go into it? Well, obviously that doesn't help us because there's no reason to factor out a one. Do the other perfect squares though go into this? And she writes the list all on the left side of the screen that she's writing on. 1, 4, right? Because 4 is 2 squared. 9 is 3 squared. Okay, so if 9 goes into it, you can pull a 3 out. If 16 goes into it, you can pull a 4 out because 4 squared is 16. Okay, so maybe going through that list, 1, 4, 9, 16. 25. Like, can I pull those out? That's another strategy you might have rather than just finding twos, which is what the very first video I got for you here. I just want to find your approach and to make it efficient over time. Okay, there's our answer there. 18 is the last one I'm going to go over for you guys. But again, feel free to email me questions, right? Ask me. I'm willing to bust out another video for you individually. And I can share it to the group if I'm just like, I think a lot of people could benefit from this. But anyways, number 18 is here. Last one here. Again, what are we doing? Pythag, baby, Pythag, because the sum of the squares of the lengths of each leg equals the square of the length of the hypotenuse of a right triangle. And we have a right triangle here. We got a couple of notes, okay? This one's a little bit harder because we don't know what a leg is and we don't know what a hypotenuse is. We just know that the hypotenuse is twice as long as this leg here. Ooh, we're gonna get a theorem coming up pretty soon about this one. The hypotenuse is twice as long as one of the legs. We're gonna learn something. We're gonna be able to do something very cool about this. But anyways, right now we're just trying to figure out the lengths. What are we gonna do now to sort of prove the answer on this one here? Well, let's make this one A. I like A being our shorter leg. I just do. It doesn't have to be. Make this one B, and let's make this one C, right? The important thing again is the hypotenuse is C. Okay, so we got to do x squared plus 5 root 3. Okay, remember that whole thing, that whole action. That's why they're having you practice this up here, okay? Because you're squaring the whole thing, Don't stop squaring. Square the whole thing right here. 5 root 3, the whole thing gets squared. And then 2x squared, okay? So substitute in parentheses. I'm sure people make mistakes with this. They'll put the 2x here and they'll square it and they'll just square the x part. No, you got to square 2x. You don't just square x, you square 2x. You square the hypotenuse because this is 2x by 2x, right? And so then the inside here, 2x times 2x is 4x squared. That's what the square of the hypotenuse would be there. So this is 4x squared. Okay, we still have an x squared hanging out right here. This is 5 squared, which is 25. I'm going to do this a little bit quicker than I did this stuff earlier. 5 squared is 25. Root 3 squared is 9, so we'll multiply that times 9, okay, right? This is just 5 times root 3, but if you square both of them, it's now 25 times 9. And we got 4x squared over here. So what we can do is we can start moving our variables to one side of the equation, okay? Eliminate that x squared. And combine like terms over here, which combine our numbers. There are constants that we have right here. 25 times 9, well, 25 times 10 will be 250. So 25 times 9 will be 25 lower than that. So that's 225. And that's going to equal 3x squared. Okay. Now, right, you might be thinking, well, should I take a square root here? Take a square root of this whole side, square root of that side? No, because then you'd have the square root of 3. Which doesn't help you at all, right? That's just an irrational number you're introducing here. You got to get rid of that 3 somehow. So start away from the x. What I like to say is look at this here. X is being squared first, and then it gets multiplied by 3. Right? By our PEMDAS rule, this is x squared, and then you multiply it by 3. So you want to get rid of the thing that happens to x last, right? Kind of reverse PEMDAS. That's how I recommend you solve things, okay? So x squared times by 3 means we're going to knock off the thing that happens to x last, the thing away from x, okay? This x as the square thing, it's just, you want to square it so bad. Ignore that for a second, just get rid of the 3. Get rid of the 3, simplify. There's a reason why they say the word simplify. And then this is messy, right? You're like, oh, I simplified this, but then this got messy. What? Because this has got messy. I was trying to simplify it and it got messy. The reason why this is messy is that 3, I don't think it goes into 225. No, it does. Yes, it does go into 325. Oh, wait, 9 goes in there. Yeah, if 9 goes in there, 3. Anyways, one way I can tell if 3 goes into this is actually a neat trick. If the digits of a number, you should listen to this. This is a neat trick that I always tell everybody every year. I don't know if I'll have time for this, but if the digits of a number add up to 9, that number is divisible by 9. So 9, divisible by 9, of course. 18, 1 plus 8, 9, divisible by 9. Yep, it's 2. 227, 2 plus 7, that's 9, divisible by 9. Yes, sure, it's 3. 36, 3 times. What? So 225, 2 plus 2 is 4, plus 5 is 9. Okay, so it is divisible by 9. So that, therefore, what would follow from that is that's to be divisible by 3 because 3 goes into 9, right? 2 times. So, anyways, this actually isn't going to make things quite as complicated here. All right, why does that work with the 9 thing too? Well, 9 is 1 less than 10. And then if you double it, it's going to be 2 less than 20, but we'll have another 1 in front. And then if you double it, if you put another 9 up here, it's going to be 3 less than 30, but then we'll have a 2 in front. So it's always maintaining that 1 kind of below 10. Wild. All right. So anyways, let's check it out here. 225 divided by 3, and we get 75 here. And there we go. So it's actually not as messy here as I thought. 75 equals x squared. We got that here. So now we have to take the square root of both sides. Here, do your tricks, right? Some of the other people are developing different ways, right? That's okay. I'm here to support you through the process and hopefully find something that works for you. Square root of 75, you might be thinking, okay, can't divide by 2. Can I divide by 3? Yeah, you can divide 75 by 3. What can you divide it by? So maybe you just start doing that. Okay, I can divide 3. So 3 goes into that 25 times. And then you're thinking, wait a second, what do I know about the number 25? Okay, I would have probably approached it backwards, like backwards from that, not just like pulling out 2, because 2 doesn't go into 75, 75 is odd. 3 goes into it, 4 wouldn't go into it. So I would have gone through the perfect squares. Does 4 go into 75? No. Does 9 go into 75? No. Does 16? No. Does 25? It does. Good, because 25 goes into it 3 times, and we can take the square root of this, right? We can pull that out of the radicands, right? Evaluate just this portion of our radicands, take the square root of 25, and that would equal 5. And we still have a root 3 inside, and there we go. We have our x. So we have our hypotenuse, or not hypotenuse. We have our leg right here. We have our leg right here. Our leg here is 5 root 3. Oh, interesting. Did I do this wrong? I think I did this wrong. What did I do wrong here? I made a mistake. And let me see where my mistake is, because it just shouldn't be isosceles. What did I do wrong? Oh, gosh, Mr. Fortin. I shouldn't have gotten 5 root 3 at the end. So what did I do wrong here? Let's see, 9, 25. I have to get the Jamboard to figure out what we did wrong a little bit later. Did I multiply this wrong? No. That's right. What did I do wrong? This is awful. Oh, 5. Yeah, 5 root 3 is x. I think this is just a flawed problem, to be honest. This shouldn't have been 5 root 3 because we're actually going to learn something. Oh, is it Lex? No. Let's look at the book. I think they actually wrote a bad problem for you, and maybe we can talk about why this was a bad problem later, because I don't think I made any mistakes on this. Let's check it out. Oh, I did make a mistake. What did I do wrong here? X is 5. So this is definitely 3x squared. Wait, hold on. X squared, yeah, 4x squared. Did I do this wrong? 25 times 9 is 225. I'm glad I'm not doing this in front of a live class. Well, somebody probably could have bailed me out at this point in time. 225, okay, so let's see, 4x squared equals x squared plus 5 root 3 squared. So yeah, they got the right answer in the book. Logically, it makes sense to me, but I'm not seeing the mistake that I made here. So this is 225 for sure, because 9 times 25 would be 225, yes. And then divide both sides by 3, 225 divided by 3. All right. Message me if you see what I did wrong here, because the answer to this legitimately in the textbook is 5. Okay, x equals 5. And let me just double check this one here, because if this is 5, let's just double check this one here. 5 squared plus 5 root 3 squared equals 2 times by 5. That's what squared. Sorry, 2x squared. 2 times by 5 squared. Okay, so I'm just checking this in the Pythagorean theorem to see if their answer was correct here. 25 plus, and it is, right? I've done this a ton of different times here. So 25 times by, oh, I see my mistake. You probably noticed it way before I did, okay? So that's why I was going in to check my answer. Let me put it back up here. So my mistake here, and this is it, I'm putting it back in the Pythagorean theorem to be like, well, I know this is the answer. Why does it work? A mistake that I made here was this. Got our C right here. And I was like, 5 squared is 25. Root 3 squared is 3, not 9, not 9. The mind is a beautiful thing. I love making mistakes. It's great. So anyways, hopefully you stuck around this video with me. I keep these mistakes in there. Mistakes are wonderful. They're great. Your best learning opportunities. Mr. Thornton needs to learn. So anyways, this is 3. Okay, this is 3. And hey, I was able to talk about, the little 9 trick, that I talked to you about here. But I wouldn't have talked about this because I wouldn't have gotten to 225 here. All right, 25 times by 3 is 75. Okay, and yeah, if I just divide 75 by 3, I get 25, which is a perfect square. So I can ignore all this garbage, right? Get back up here, square root of 25 equals x squared, so that means x is going to equal 5. All right, thank you for watching. Hopefully that didn't drive you crazy that I made a mistake there, but if it did, live and learn, right? Roll with it. It's all good. Email me if you have any questions. Take care.